Hey everyone, welcome to today's explainer on section 11.2. So we're going to be looking at reliability requirements today. And if there is literally one thing you take away from today's session, it's this. System dependability doesn't just magically happen because you're an amazing programmer writing bug-free code. I mean, we all wish it were that easy, right? But it actually requires meticulous attention to detail right at the very beginning when you're figuring out your system requirements. Because if your requirements are flawed, well, your perfect code is just going to perfectly execute a completely flawed plan.
Here's our roadmap for today. We're going to kick things off with the Warsaw airport crash, then look at the types of reliability requirements, dig into the 3 key reliability metrics, talk about how to avoid overspecification, look at functional reliability specification, and then wrap it all up with a summary and some exam-focused tips. Let's get to it. Starting right in with Section 1, the Warsaw airport crash. We're beginning with a pretty dramatic historical case study from 1993, and it perfectly illustrates the absolute life-or-death stakes of software engineering. So picture this. It's September 1993, and an Airbus is landing at Warsaw Airport in the middle of a massive thunderstorm. The plane touches down, but for 9 terrifying seconds, the computer-controlled braking system just doesn't work. Nothing. Why? Well, the software completely failed to recognize that the plane had actually landed. It literally thought it was still airborne. Because of that, a built-in safety defense mechanism stopped the reverse thrust from deploying. Now, reverse thrust is what slows the aircraft down on the runway, but deploying it midair would be catastrophic. So the plane basically acts like it's still flying, runs right off the end of the runway, hits an earth bank, and catches fire. Now check out this quote from the official inquiry. The really terrifying truth here is that the code actually operated exactly as instructed. No, really, there were absolutely 0 errors in the control system's code. None. But the software specification itself was incomplete. It just hadn't taken into account the incredibly rare aerodynamic and weather conditions of that specific landing. So this proves beyond a shadow of a doubt that you simply cannot achieve dependability if your initial requirements are flawed. You've got to get those requirements right first. All right, moving on to Section 2, types of reliability requirements. So, to prevent disastrous disconnects like that Warsaw crash, we really need to divide our system requirements into 2 distinct categories. We break these down into functional and non-functional requirements. Functional requirements basically dictate the actual behavior of the software to ensure safety. It's the what the system actively does. You know, things like checking inputs, maintaining data backups, or executing recovery protocols. On the flip side, non-functional requirements define the strict mathematical probability of uptime or failure. Think of it as the numerical target the system absolutely must hit, like a 99.9% uptime guarantee. Basically, before you can build all those functional safety nets, you've got to define your non-functional mathematical targets. Which brings us to Section 3, the 3 reliability metrics. This is honestly the absolute core of today's explainer, the specific mathematical metrics we use to quantify those non-functional targets. Because as a software engineer, you can't just wave your hands and say, hey, make the system reliable. You have to quantify it using one of these 3 metrics. First up is POFOD, or probability of failure on demand. This metric defines the exact probability that a system will fail at the precise moment a demand for its service is made. We use this in situations where just one single failure on demand could lead to a massive disaster, completely regardless of how rarely that demand actually happens. To make this super concrete, let's look at an emergency shutdown program in a chemical reactor. This is a perfect example. This system might just sit there, totally idle for 10 whole years. But if that reactor overheats and someone smashes the emergency stop button, it absolutely has to work. So if we specify a POFOD of 0.001, it means we are accepting a 1 in 1,000 chance of failure upon that single critical button press. Our second metric is ROCOF, which stands for Rate of Occurrence of Failures. Now, while POFOD looks at a single isolated demand, ROCOF sets out the probable number of failures you're going to observe over a very specific time period, or maybe a specific number of system executions. So ROCOF is absolutely perfect for systems with regular, continuous demands. Think about banking transactions, right? A bank might specify a ROCOF of 10 failures per day. That means they accept that out of millions of transactions, on average, 10 might fail and need to be resubmitted. On the flip side, if the absolute time between failures is what matters most, we use its reciprocal, MTTF, or mean time to failure. This measures the average time between crashes. It's totally vital for continuous tasks like CAD modeling. I mean, you want your MTTF to be way longer than a user's average working session so they don't lose all their unsaved work. That would be a nightmare. Finally, we have AVAIL, which is just short for availability. This is the probability, or basically the percentage of time, that the system is fully operational and ready to deliver its requested services. Whenever users expect continuous, uninterrupted service, like a telephone routing switch, for example, availability is going to be your primary metric. This breakdown really puts things into perspective. It shows what these percentages actually look like in the real world over a 24-hour period. So 0.9 availability, that means 144 minutes of downtime a day. 0.99 gets you down to 14.4 minutes. But look what happens when you demand 4 nines, or 0.9999 availability. That equates to a staggeringly brief 8.4 seconds of permitted downtime in a whole 24-hour period. Just think about how long a server takes to reboot. You literally can't even restart a system with 4 nines without blowing through your entire daily downtime budget. Wild, right? All right, jumping into Section 4, avoiding reliability overspecification. Because a really common trap for students is assuming that higher is always better. You know, why not just slap a 99.999% availability requirement on everything? Well, that leads us to the very dangerous trap of overspecification. The thing is, exponentially higher reliability targets require massive, skyrocketing development costs. You have to be pragmatic. Let's look at a banking ATM network. Banks are totally fine accepting a lower software availability target for an individual ATM terminal. Why? Because mechanical faults or just running out of cash will probably take it offline anyway. Spending millions to ensure the ATM software literally never crashes is just a massive waste of money. But they absolutely demand ultra-high availability for their central account database, because if that database goes down, every single ATM in the entire country goes down with it. So it's a delicate balancing act. And that leads us perfectly into Section 5, Functional Reliability Specification. Once we have our mathematical targets logically distributed and defined, we actually have to implement functional requirements to build that reliability into the system. We do this through 4 key functional steps. Step 1 is checking. This means writing code to rigorously verify input ranges so that bad data doesn't just completely break your system. Step 2 is recovery, establishing protocols like redundant servers so your data isn't lost if a crash actually happens. Step 3 is redundancy. This is using architectural strategies like N-version programming, where multiple distinct versions of a component run simultaneously. And step 4 is process, mandating really strict development rules, like forcing developers to use static analysis tools to catch errors before the code is even compiled. Okay, we've covered a lot of ground, so let's head into Section 6, Summary and Exam Focus to wrap things up. Let's solidify the absolute critical concepts you're going to need to memorize for your exams. Ensure you can clearly define all 3 non-functional reliability metrics: POFOD for single demands, ROCOF for regular occurrences, and AVAIL for overall uptime. Also, you absolutely must be able to explain the financial dangers of overspecifying reliability requirements. Remember, defining these targets is always this delicate balancing act between safety, user satisfaction, and massive engineering costs. I want to leave you with this final thought to chew on. If a software component inevitably fails, how does the underlying architecture ensure the entire system doesn't just collapse? It perfectly bridges the gap between today's lesson on requirements and our next explainer on fault-tolerant architectures. We know we can't make software perfectly reliable, so how do we design systems that survive when those inevitable failures occur? Keep that in mind as you review your notes. Thanks for joining me for this explainer, and happy studying.